Hello, so I'm going to look at this first work solution. So let's take a moment to look at what we got. So on the right hand side here, and I'm using a mic, by the way, a fine mic, a Camtasia, and I've selected just a portion of the PowerPoint screen. I'm not running the actual PowerPoint. So anyway, let's start. So we've got a hinge here, so I'm going to have a reaction at the hinge going horizontally, and I'm going to have a reaction going vertically. I could set, because it's a hinge, you can set those reactions to be pointing any sort of directions you want. You could have the normal reaction pointing going from right to left or from left to right. It doesn't make any difference because when we're at hinges, we're allowed to have negative reactions. Whereas this is a pivot on some roller wheels, so there's no sideways reaction force here allowed. If there's any sort of force trying to drive it slightly to the left, it will move. Okay, so there can be no reaction in that direction. Yeah, but although it doesn't really matter, the general convention is that let's decide what's a sensible coordinate system, and we would assume that a sensible coordinate system is going to be going from left to right for the horizontal, and from bottom to pointing up in the vertical. So we're left to right for the horizontal, and from bottom to pointing up in the vertical. So we'll set the reactions to be going in those directions that hinge. We'll have one upward reaction at this pivot here, and we've got these three concentrated loads along the bar, which we've been given the coordinate positions where they are. So one is 1 meter away, and then one is 4 meters away, and this one here from this edge is going to be 7 meters away, and so on. Okay. So what we want to do is go from our diagram here to a free body diagram. So we're going to start getting rid of these devices and replace them with what we represent the forces at those particular points going to be. So let's replace the supports with appropriate reactions. So we'll get rid of the supports there in this slide, and the first one I'll replace is the slidey, the reaction sliding roller. So there's only one reaction pointing straight up, and notice I've decided that's going to be my point A, first point of interest. So my reaction is going to be described as R subscript A. Because this reaction is going to be pointing straight upwards in the Y direction, I'll call it R subscript A Y. So that's now replaced the hinge. So that was going to be made up of two reactions. Okay, so we don't need any more reactions for our pivot that was on the roller section. I only need one there. So here, I would have put my my Y reaction at that point there, but it's fair enough. So I'm going to have one reaction here, like a pivot thing, and I'm going to have the other reaction here from left going right. So this is my point B of interest. So notice that you go R subscript B, R subscript B. So this one here is going along in the X direction, so it's going to be R subscript B X. And this one is pointing upwards, so it'll be R subscript B Y. Okay, so now we've got forces going down, and we've got these reaction forces. Remember, these are forces as well. So these forces have to balance these forces because this beam isn't moving. So a hinge has both horizontal and vertical reactions. There might be some cases when you want to incline this or skew the reactions, but they're always going to be 90 degrees of one another. Okay. So here, what we're going to do is consider some steps that we can now resolve our forces. The first one we'll resolve is the forces in the x direction. So notice I'm going to use the notation. I'm going to sum forces in the x direction, and I expect them to be equal to 0 because the acceleration of the beam in the x direction is 0. It's not moving, nor is it accelerating in the x direction. So force equals ma, in this case a equals 0. So we're going to sum up forces in the x direction, and we're not going to get anything particularly interesting. So the only force that we can see is the force RB. So go back to that slide there. You can see the only force on this diagram is this RBX force, I should have said. RBX force. So that's the only force. So that must mean that the RBX force equals 0. Let's add up our forces now in the y direction. Notice we're using this notation here as well. You don't have to, but it's good notation to use. Have a little arrow. And what we're defining here is which way is positive. So I'm defining anything going from left to right as positive, anything going from bottom to top as positive. So we're going to sum up our forces. Notice it's going to have them all on the left hand side, and then I'm going to equal that to 0. Okay. So let's go back to our diagram. So we can see that we've got force going this direction. So it's going to go in a negative sense to the sense that we're supposed to be summing up. This one here is also going to be negative. This one here is going to be negative. And we've got this force here, this reaction force, which is going to be positive going upwards. And this reaction force here going to be positive going upwards. Okay, so let's see what happens. So we've got our first negative force, minus 20. So notice what's happening here. This is happening here. This is a normal convention with beams, is that you start with going from left to right. So you see your first force going downwards. That's the first one we're going to see. We see our second force going downwards. So we're going to add that. We start at the top. And then we see another force going upwards. Then we move along. So we're scanning through the beam from left to right. And next I see another force going downwards. And then I see this final reaction going upwards. So when I come to sum my list, so I've now got minus 20, minus 40, the reaction RAY going upwards, the reaction minus 30 going downwards, reaction RBY going upwards, and that all equals 0. So notice you put everything on the left hand side. And our general convention with algebra is we have the unknowns on the left hand side, so we'll collect them together, and the knowns we'll put on the right hand side. So 20 plus 40 plus 30 hopefully equals 90. The next thing is to take moments. So I should have shown you that because we need to think about where we're going to take moments. So we could take moments at point A, or we could take moments at point B. Now, generally speaking, there would be the odd case when you shouldn't want to do this, but generally speaking, you'll want to take moments at the hinge. What's the advantage of that? Well, remember that a moment is a force times distance. So the distance away from the central pivot of the moment, which is going to be this point here. So the distance away for this reaction force here to my pivot is 0, and this one here, 0 force times 0. So I've got rid of two forces in my equation. and I've only got them one unknown. That's the advantage of taking your moments at a hinge, generally speaking. There are some times when you don't want to do that for some reasons. Okay, so we're going to take moments, and we're going to use this notation. And I'm going to tell you that anything that's going a force going around in a clockwise sense around B is going to be considered positive. So I'm going to sum up my moments, and all that stuff will be on the left hand side. And again, because it's not rotating, it's actually I times alpha. It's moment of inertia times angular rotation. So we've got no angular acceleration. We've got no angular acceleration, and that equals 0. We've got no rotation, so that's what we're saying on the right hand side. So if we go back and look at our forces here, so what we need to do is measure this distance from here to here, see that force is going perpendicular from that distance, so that's a distance of 9. That's going to be going anti-clockwise, so that's going to be a negative moment. This distance from here to here is going to be a distance of 6. It's going in a clockwise sense, so it's going to be a positive moment. So we're going to have 6 times RAY. Then we'll have 6 times 40, and that will be going in a negative direction. It's going anti-clockwise. And another one here, which should be going anti-clockwise. So that's what we should be looking for on the next bit of the solution. So here we've got them. So notice I've put the force first, times it by the distance. So I've got, and then I've put the fact that it's a negative. So the first force is 20, times it by its distance away from the pivot, and it's going to be going in an anti-clockwise sense. And then we've got the second one, then we've got the reaction, which is going in a positive sense, and then we've got the last force there. So, get my calculator out. I don't want to do this algebra. Get my calculator out. 20 times 90 plus 40 times 6 plus 30 times 3. Stick it all on the right hand side, and we end up with 510. So 6, I could put that in front of the RAY. So 510 divided by 6 equals 85. So I found this bit of the solution. Okay. So next thing is to go back to my equation 1 and to substitute it into my equation 1, and then we can find out what the RBY is going to be equal to. So let's substitute equation 2 into equation 1. And we see that RBY is going to become 90, take away 85. So RBY equals 5 kilonewtons. So my final solution should look like this. 85 here in the sort of middle of the beam, and 5 here at the end. Do a quick sanity check of your answer. So basically we're saying that there's a lot of force here, suspending all these forces pushing down on it, and there's just this little bit that needs to sort of counterbalance it. You can imagine this would be like a plane or something like that. A lot of forces with a wing, and then maybe a tail section at the end, applying a little force at the far away. So yeah, so we've got most of these forces here, kind of pretty much balanced as well. So if that was 30, that would all be balanced, and this would become 0. So that all seems to, going through a sort of a kind of an sort of engineering sort of sanity check of our solution. It all looks pretty good. You could do a final check as well, like sum up these numbers.